Thank you so much for the nice introduction, and thanks for inviting me to come here. It's a fantastic place. I've never seen such a big institute just for nanotechnology. It's really impressive. So in the first couple of slides, I wanted to brag about our institute, but I think it's a little bit shame on me now because it's a small institute compared to what you have here. So since this is a nanotechnology institute, I chose a subject which relates to nanostructures concerning my work. And I just show this is the Liquid Crystal Institute, which this building was built, I think, 1996. And probably if I press something, it will show something. Okay, here you go. Okay, and just in case you don't know where is Kent, I have a Google map, and that shows Kent. And Kent is right here. So it's not far from, I don't have Waterloo here, somehow it just showed Kitchener. So in other times, I used to say that you can see that Kent is this geometrical center of an area characterized by cities like New York City, Philadelphia, Chicago, Detroit, and now I can say and Waterloo. So it's the center of this area if we look at from that point. So the Liquid Crystal Institute was established in 1965, exactly 50 years ago. So we just started the 1 year programs of celebrating 50 years, and it was started with this guy, Glenn Brown, and it's called Glenn Brown Liquid Crystal Institute. And he organized the first 4 international liquid crystal conferences, and the next one will be in Kent again, just to show that the 50 years after almost 50 years, it comes back to Kent. And okay, the Liquid Crystal Institute is famous about the first patents on liquid crystal displays and other applications were patented at Kent State. And this guy is called James Ferguson. He was the first one who patented this liquid crystal temperature sensors. So you can put on your forehead or measure the temperature of the bath and so on. And also he patented the first twisted nematic displays, which and he started the company, first made this kind of wristwatches, and only people the age similar to mine will remember that at sometimes you can have this wristwatch. And then later, of course, this was developed to be a display, and now we see much nicer displays, 4K, 8K, I don't know how many, and sold by LG mainly and Samsung. These people who are actually now vice president and heading the liquid crystal technology in LG and Samsung, they all got PhD in Kent. And so there was the research contributed to laptop computers, cell phones. They all have liquid crystal TVs or displays, switchable windows, and so on. And some recent examples, we have a couple of spin-off company. This is Alpha Micron. They are making these goggles which can change the transparency in milliseconds, so much faster than photochromic glasses. And that's a so-called boogie board, which is a paperless writing tablet. These are relatively new development. And we also have a graduate program, no undergraduate program like here, but we have a chemical physics interdisciplinary program which offers PhD and master degree. So far we graduated more than 170 PhD degrees granted, and in the last couple of years, lots of students get jobs directly by Apple. So we used to call Cupertino as Kent West, or something similar. And we are really proud of them. I don't know if you have iPhone 6, that has a very special display. All the previous displays used rubbing, mechanical rubbing the substrate. This is the only one which used photo buffing, which interesting thing I remember was used to teach them that this is a technology developed in early 90s, and by 2015 they made it. And so this is really nice thing. And now this year we just started a new program. It's a liquid crystal engineering, in case anyone would be interested in. It's a master program which will start this fall. And if you want to see more, you can see on the website. Okay, so what are liquid crystals? I'm pretty sure that most of you know, but just in case someone wouldn't know, this is a very old state of matter. I think this is the first state of matter which was officially discovered, not known by the ancient people, that that gas and solid and liquid crystals are in between the isotropic liquid and the solid state. So these are some kind of organic material. It was discovered in 1888, so a long time ago. And so some organic materials, I will show you later, if you heat, sometimes they just go to a milky-looking fluid state, which now we call nematic liquid crystals. And those nematic liquid crystals are used all these displays right now. And if you heat more, then they become clear, and then they become transparent fluids. So, and some of them before would go to this one, or instead of going there, it goes to a gooey state of material, which is known as smectic liquid crystal. Smectic means soap, and it really is similar to soap. And that's actually the first nanostructured liquid crystal. And so for more technically inclined people like you, think it's so you can imagine that liquid crystals are just basically for physicists. Chemists is more complicated. But physicists just consider as rods, and then you have a bunch of rods, and you can imagine that you can you put them randomly, oriented randomly, and also if the center of masses are all randomly positioned, then it's a fluid. And it's an isotropic fluid because from any direction it will look the same. A nematic liquid crystal is also fluid in the sense that the center of masses are randomly distributed, but it has a director, which we call N, which points to the direction of the average average molecular direction. And this is a three-dimensional anisotropic fluid. An example of a molecule which makes this phase, this is a 5Cb. It's the most known used liquid crystal. I heard that even in this building or in this university, people are working with 5Cb sometimes. Actually, in a real state, the molecules make dimers because the cyano group is polar, so they point to each other and they rather make pairs. And actually, that's how they look. In some materials, which are the smectic, they are two-dimensional fluids. In the center of masses are random only in 2 dimensions. In the third dimension, they make a periodic structure. So this is the first nanostructure because you have a nanoscale periodicity of a few nanometers. And a typical molecule which would make that phase is shown here. So you have like 2 benzene rings, which is considered to be a rigid core, and some aliphatic tail, which is flexible. And this is really important to make the layering, because there is a nano-segregation. The core, rigid core, would like to be near to another rigid core, and the flexible tail close to a flexible tail, so that makes this layering structure. That's driving. This is the simplest nanostructure, which is known for about 100 years, I think 1915, when Friedel identified that phase. And of course, if you cool further, eventually they all crystallize. So again, the flat panel displays use twisted nematic liquid crystals, or now they use other methods, but still nematic. So since I will be speaking a little bit more on smectic phases, I have to show that there are at least 3. There are actually like 40 different kind of smectic phases. The most abundant is the smectic A, which is called orthogonal. So the layer normal is the same as the director. So it's a non-tilted structure. This is smectic A. There it can be tilted with respect to the layer normal. That's called smectic C. And it can be tilted in the same way in the adjacent layers, or it can be tilted in an anticlinic way. So that's, it can be synclinic or anticlinic. And there is, as I said, there are more variants. But just wanted to illustrate that there are so many phases. Actually, there are more than 100 liquid crystal phases, states of matters between the liquid and the crystal. And so it's amazing. Another important concept is the chirality. So for example, you can make 5 CB chiral if you have a stereocarbon in the tail here. And this small change will make important changes in the structure. Instead of forming a nematic, it forms a chiral nematic, which is a helical structure. It forms a helical pitch, which is in the range of 0.1 to 100 micrometer. And then if it falls in the range of the visible wavelengths, then it can be used as a thermosensor, as I showed you the Ferguson's patent back in 1968, I believe. So because it just relies on the fact that the helical pitch is in the visible wavelengths, and then it changes with temperature. So you have a Bragg reflection, and then you can see the color is changing with the temperature. And you can make formulations which change very precisely, just within 1 degree, the whole spectrum, or you can set it as you wish. There is a mixtures which you can buy, and then you can mix that way. So, and other thing which people do here, and everyone knows, is X-ray scattering. We have to study the nanostructure. X-ray is one of the most important technique. And here I just have a demonstration what kind of patterns you will see, a 2D pattern of an X-ray. This is the wide angle range, and this is the small angle. The small angle is in a frame, red frame, because that's what I will show here, that in that range. Because the wide angle range shows the distance between the molecules in basically the lateral distance, the ridge distance, and the length of the molecules, or the layering, or more layers, are seen in the small angle. So this is an isotropic liquid. It is very diffused. Sometimes you don't even have any peak in the small angle. A nematic liquid crystal can be aligned. If this is in magnetic field, it can align, so it show an alignment for this direction of the lateral directions. And in lots of cases, you see kind of peaks, or not, it's a diffuse peaks, which are due to nanoclusters. even in nematic phase, a very short range, you have layering, and then you can see it by X-ray. And especially will be true for one of the material I will show. And the smectic A material, you see sharp peaks in a small angle, and in the smectic C, you see 4 of those peaks. They are situated at an angle theta, which is the tilt angle. With respect, this would be like the magnetic field direction in this horizontal direction. And the other technique which we have to use is the TM, and you also have TM here. So again, I don't say anything new. We recently got this 200 kilovolt microscope, and this is important thing that it has a low dose mode, and we also have an ultramicrotome and a freeze fracture TM. The low dose mode is very important when you would like to visualize thermotropic liquid crystals. Those liquid crystals are showed as so-called thermotropic. They change their property with temperature. There are also the lyotropic liquid crystals, which are more relevant in biology. Everything in our body, almost everything is in liquid crystal state. But I'm just talking about thermotropic. So you picture it, you have a molecule, single molecule. That's a challenge if you can see the nanostructure of a single compound material, because you expect not too much of a contrast. But and the one challenge is that it's organic material. So if you look at it with the shine with the electron beam, it will kill it very quickly. So you have to use low dose. And so this is the principle how it works. And this is just, we use copper grid, everyone knows, and then we can check the thickness based on birefringence. And the main principle here is shown here. So if you see this, I think it's a vineyards, and if you look at it from the top, then you see the rows individually. But if you look at from some direction, the individual rows will not be visible. You see a uniform texture. And so basically, what you see, if you look at it, if the layers are parallel to the electron beam, then in some part it goes through the core, which has benzene rings, so it has more electron rich than the tail. And so it will be darker here, and it will be brighter and darker. But this works only if these guys are almost exactly perpendicular or parallel to the beam. If they rotated by more than 3-4 degrees, then you will see nothing. As you see here, it's no contrast. So the first question, if you can see rod-shaped smectic liquid crystals, and you see the layers, and it's very well visible, and then you can calculate the layer spacing, and then you see directly what X-ray shows you, and you see more things. For example, if you look at it very carefully, then you can see that there are defects. Here, this is so-called edge dislocation. People couldn't see edge dislocation in liquid crystals because it's a nanoscale. Optically, you cannot see that. And here is a split core edge dislocation. These are just very new things we just observed recently. And you can analyze that these things are actually asymmetric, and people can learn a lot. So this is not the point to show that. I'm just to point to show that you can visualize layers in a single compound material. But the material we are interested in, and I've been interested in for 1997, I think, is the band-shaped liquid crystals. So all the others we talked about just rod shape. Now, if you make a small kink in the molecule, that will bring in lots of interesting things. So this is a typical molecule. It's somewhat larger than the other. There is 3-ring band core, but you typically have 5 rings, and then you have tails here. So this angle is typically 120 degrees. That's the opening angle. So because of this kink, now what happens, they tend to form layers. So this is just one layer. They can form layers so that it looks like a smectic A, because the director, which connection of the 2 ends of the molecules, is parallel to the layer normal. And so, but because they all pack in the same direction, they become polar. So it's just like when you have bowls in your kitchen shelves, you put them all in the same direction. You cannot put them in all kind of directions because it won't be stable. They want to fill the space efficiently. So they become spontaneously polar, which is very important because you have a ferroelectric material without the need of chirality. Before, ferroelectric liquid crystals required chirality. And if you do chemistry, you know that chiral chemistry is much more expensive than non-chiral. So this is one interesting thing. And these, if you put the layers after each other, these will illustrate different phases. But you can, the polarization can go in the same direction or it can go alternatively. So it can be a smectic APA, which is anti-ferroelectric, or smectic APF, which is ferroelectric. Another interesting thing appears if they become spontaneously tilted, like the molecular plane is tilted with respect to the layer normal, then they become chiral, not only polar, but they become chiral. But now the chirality is coming due to the polarity and the tilt. And this specific phase has 4 subphases. It can be anticlinic, synclinic, ferroelectric, and antiferroelectric. So 2 times 2, 4 possibilities. There's another option if they are leaning, not or tipping. They are not tilted in that way, but in this case, the polarization will not be parallel to the layers. It also has 4 possibilities, and there is, and the last possibility concerning smectics, that it can be double tilted. And this has 8 subphases. I didn't even want to bother you with those. So just the smectic phases from band core liquid crystals can have 8, 10, 18 different phases. And they can be distinguished with different ways. So just the smaller kink brings in lots of variety. So this is known since 1994, but after it became known, it turned out that, of course, it's already been synthesized in 1916 by Forlander, who was a German chemist who synthesized more than 4,000 liquid crystals in the beginning of the 20th century. So, but he never recognized that this is a band core. So just to illustrate that what kind of interesting properties they have, they form freestanding filaments. And some of them are just very thin. What is their thickness is just determined by the material. What is really interesting that even a nematic phase from this material, which sometimes it forms nematic, can form filaments. And their aspect ratios is basically unlimited. Which, why do I say it's interesting? Because we know for a long time that we know the Plateau-Rayleigh instability for Newtonian fluids. It's known that if you have a bridge of a fluid, it cannot be longer than the perimeter. Okay, so the aspect ratio, this is lambda over the diameter, it cannot be larger than pi. So otherwise, if you make a bridge, a fluid bridge, it will be unstable and it will just drop down. You cannot stabilize. But here you have a fluid, it's a 2-dimensional fluid, but nematic is actually even 3, and you still can make filaments. So something is very strange. So in general, a 3D fluid usually forms stable droplets, and a 2D fluids from stable films like smectics usually can form very nice two-dimensional objects. You can make just one layer freestanding and just as a membrane. And columnar liquid crystals, which I didn't show you, which are one-dimensional fluid and two-dimensional layer structure, they can form fibers. That was known. But these smectic and nematics is astonishing and kind of. And so this is a bridge. And the video, I just noticed it didn't work for some reason. Some codecs is missing. If you apply voltage here, you can shoot the material back and forth. It's polar. It's polar material. You can just shoot them. And this shows that as they form fiber, you can even stick some ball on it. It's like a necklace. And then using the angle and using the weight of that, you can determine the tension. Some of these single filament can measure a force of about nano-Newton, just basically hanging on them. And I have a video which would show if you apply field, then you can vibrate them and so on, which doesn't work. Okay, and so maybe this video shows, and you can break them. Because they are fluid, so you can break, but sometimes it's not easy to break. But if you break them, they are recoiling, and it's an interesting. They recoil. It kind of has an Euler buckling, and then they have a helical structure. And although the molecules again non-chiral, but you can see that there is some helical behavior. So based on those experiments, we kind of realized that the structure is quite complicated. It's again just one single compound, but it has two kind of nanostructure. One has about 10 nanometer periodicity, and the other one here, the layers are concentric layers, which have about 4 nanometer periodicity. And this periodicity makes them stable. It's like if you have a spring wrapped around a fiber, and this makes it springy, and it's completely stable. And so how about their TM structure and X-ray structure? So I hope I showed you that they are quite unique material. Mechanically, they behave interestingly, not as a usual material. So one needs to figure out what's the nanostructure. So this is just a normal smectic A phase of this 3-ring material. You see that there is only one peak on each side in the smectic A. So it's not. This peak, what you see, is a Fourier transform. If you have one peak, it means that your distribution is like sinusoidal. But still, you can see quite visible. You have darker and brighter area. Actually, the resolution is about 0.7 nanometer. We almost see the molecules. We almost see. We are working on to have some mathematics algorithm to make it more precise. And I said that I showed you that they form smectic phases because of the kink. They don't want to translate with respect to each other. But some of them, if you have some interestingly, nothing very special. This is just a larger opening angle. They form a nematic phase. But what is interesting, you can see this 4-lobe structure. So you see that there are smectic clusters in it, and the correlation length is about 20 nanometer. So these were known for rod shapes, but only in very, very narrow range above the smectic. And this goes in the whole nematic range. even in the isotropic phase, you see smectic clusters in that. So question if we can see it in TM. And indeed, you can see with TM at different temperatures. This is isotropic. We cannot see, and it cooled down. And you see that more and more smectic layers, small clusters, come into the thing. So we found that these materials make a very large flexoelectric effect. And it was not understood what causes that, because the normal theory explains 3 order of magnitude smaller effect than we found. And we think that the reason for that is we have these smectic clusters which are polar, all polar. So when you bend the flexoelectricities, you have a film, you are bending, and then you can generate electricity. And when you bend, you are switching over these polar clusters because they are bent themselves, more or less. And so they have a preferred direction. And so that can explain. And another kind of modulated smectic phase is when you have a very asymmetric molecules. So far, the molecules are showed they were symmetric. They were basically linked to the same kind of molecule with the benzene ring in the center. And now this one is asymmetric. And this one has 2 ferroelectric phases. They are different. And we were wondering for a while what is their structure. And you can see their X-ray picture is very, very complicated. If you see this one, it's like that. So basically, you have 2 periodicity. One is the 1, 0, and the other is the 0, 1 peak. The one is about 3, 4 nanometer, and this is 15 nanometer. And then you see the harmonics of these peaks, and then here you see the 1, 1, 1, minus 1, and so on peaks. And if you distinguish the 1, 1, and 1, minus 1, it means that you have a tilted, it's a monoclinic structure. So it has a 2-dimensional structure, but it's not really 2-dimensional because this one periodicity is much weaker than the other one, at least an order of magnitude weaker. So this is a kind of a modulated smectic structure. You have basically one periodicity, and this one get modulated. And what is get modulated is that it's a polar, and the polarization is playing, and it forms defects in this 10 nanometer scale. That's why they form filament. On the other hand, so if you look at the TM, you assume that you would see this modulation. You might see something, but it's not the one what X-ray shows. It's not the same periodicity. Mainly, there is no additional periodicity. So this indicates that this modulation exists only in bulk. TM is done on 100 nanometer film. So if you have quench it close to a film surface, then the surface can unwind kind of that modulation. So it's not very robust. It's a soft nanostructure. It's relatively easy to get rid of it. If you apply voltage like 10 volt per micron electric field, you also can unwind that. So you have a modulation, but the second modulation is not very robust. On the other hand, we don't see this modulation, but we actually see lots of defects. And this was interesting for my colleague Oleg Lavrentovich, who is expert on defects. And I used to tell him that my brain is full with bananas and bent core something, and his brain is full with defects. But he's a very smart person. He's a world expert. And you could have seen his face was so happy to see defects in nanoscale, and then can figure out that what is the this periodicity and Berger's numbers and so on. You can do some nice theory. You can even see tilt grain boundary phase. You can see screw dislocations. All these things are there, and you can see what TM. Okay, there is another set of material which has nitro groups here. It's not asymmetric like the previous one, but it has some substitution. It also, this was the first one which formed these filaments. Those pictures were done on those materials. We observed it in 1999, and still it kind of was hanging around what really going on, and you can see that we just submitted a paper out after 16 years. The first on this material were done when I moved from Germany back to the United States. I brought that material with me. I still have it, so I'm still working on it. There are some things which just coming back and then we never get rid of, and probably after I retire I still will look at this material. The reason I'm so much interested in, when you look at the polarizing microscopy images, they are gorgeous. They are just, look at this one, they're fantastic. They form helical filaments. They grow like a sword, some like a DNA, they have double helix, and some like this myelinic structure. They have periodically dark and bright structure, and this is in freestanding film. It also shows this one. So this is just really appealing how they look. So finally we were able to look at their structure with TM, and okay, this is the X-ray, again shows a very modulated structure. But in addition, what in the previous modulated, we didn't see any modulation. Now what is interesting, we don't see the layers, but we see the modulation, and we see an extra modulation. The same kind of phase, but the nanostructure is different. It's a much more robust modulated structure. And indeed, we cannot get rid of if we apply 10 volt per micron field. And some other material, it's even more pronounced. So these distances are the 16, this is 10 nanometer periodicity, and this is an extra, it's around 100 nanometer. And this is a fingerprint texture. So what's going on, I think, based on that TN, we were able to understand what happens in the microscopic textures when you see stripes, dark and bright. This is the darker and brighter stripes in the optical range. They want to make filaments inside, and they make filaments, and they want to decrease the surface tension, so they like to share boundaries with each other, so they go like that. And the same thing happens in TM. They want to make filaments, then, and in the top, at the air, they have homotropic, and here there's planar alignment. So they form this additional stripes of a few 100 nanometer, which is about the same as the film thickness. And here the 10 micron was again the same as the film thickness. So that periodicity is determined by the film. So we understand that now. Okay, there is this is the second last. Okay, I'm soon getting ready. There is a fourth kind of even more strange phase. It was a fourth band core phase. They call it B4 phase for a while, which just in 2009, which again was hanging around for since the 1990s, and it turned out that this is the so-called helical nanofilament phase. So the smectic layers break into about 8 layers, just 40 nanometer blocks, and they form ribbons which are rotating around. So you can see the free structure TM structure of those. It's a beautiful work by the Boulder group in 2009. What bothered me is that the first time we have seen this, some of the materials in the homologues 7 and 8 materials, they were beautiful opal blue. The others are transparent, I mean yellowish, but are not blue. And it was the same kind of material, just one more carbon at the tail. And we didn't understand what's the reason. We were wondering what this material can be used, and we couldn't figure out anything else, just like jewelry. And actually, I even made some small jewelry to my wife, and then it's a beautiful, just like opal, and we didn't understand why. And so we did the cryo TM, and so again you see these stripes in every 120 nanometers, which are the half pitch, how they rotate around. Whenever the layers are in vertical direction, you can see the layers. In other part, when they turn away, you remember as the layers are not upright, you don't see contrast. So they are turning away. Periodically, you see the layers, and then again, no layers. So this is 120 nanometer. It doesn't explain the blue color. And so what we see is the 7 and 8, which has the blue color. They are much more regular than this one. They are kind of extra coiling around. And what are still, of course, it doesn't explain the blue color. So this is just shows how nicely they can synchronize, even though they have this strip. So you can imagine there are a bunch of airs or empty spots, but they can synchronize. So what the important finding was is that if we happen to have some places, the film has a thickness, has a gradient. So if the film thickness changes in a short distance, then you can see some area, you just see one set of filaments, one row of filament, okay? And here you see 2 rows of filaments, and here you see 3. And you see that these stripes turning away from each other by around 37 degrees. And so what we did, we have simulated. This is a $2 simulation. I went to Giant Eagle and bought a pasta which has a helical structure, which looks like this helical nanofilament phase. And so we glued one row in the same direction on a plate, and then we added the same amount on the top, and we started shaking. And if you shake, eventually it finds the equilibrium alignment, and you can see that the second row is turned away by around 40 degrees. And then now you add another layer and shake, and the third one turns another 40 degrees. And just simply because that's how they can find the best packing on each other. And so basically you have 10 layers, 10 helical nanofilament around 35 nanometer wide on top of each other, and it makes one helix, and which is 360 nanometer. And if you multiply with the refractive index, which you have to, is 1.5, you get that you have a peak at 480, and that's what we see. So what happens is that the lowest homologues are very regular, and they can form this regular twisting away, the extra second twist. But the higher homologues are more wriggling structure, so they cannot do that. But if we go back to see, even the higher homologues has some small peaks, so it indicates that there are tiny domains where they just happen to make one regular domains. Okay, so the last one is the newest development in this liquid crystal area and the special band cores is the flexible band core materials. So far, which I showed you, they are rigid band core. There's a rigid band core in the center and then flexible tails. But you can make the other way around. You have a 5CB or something you can imagine that the normal nematic. You can cut the tail and then stick two 5CBs together and then link it with a flexible tail which has odd number of carbons. And if they have an odd number of carbons, then they end up be tilted. You see that this I think maybe 9 or so some points in this way. Of course, it's very flexible, so the thermal motion makes them flexing, and it's not really rigid. But they make a very interesting nanostructure. And this was just, again, we used freeze fracture TM and X-ray, and the Boulder group used also freeze fracture. And it showed that what happens is, so this is the illustration that it's a band. The freeze fracture TM shows a periodic structure around 8-10 nanometers. And we even have shown the so-called Bulligan arches, which shows if you see a heliconical structure from one side, you see some arches. And from that, we figured out that this is a heliconical structure. And what interestingly, if you look at the X-ray, then there is no peak at 8-10 nanometers, nothing there. So it's a true nematic phase. There's no density modulation. It's a fluid, but it has a 10 nanometer structure. And this one, so you can imagine then you have a flexible things, how you could try to put them together if you make these rings. But they always have lots of defects in this case. Here you would have a defect. Next time, again, a defect. In every 10, 20 nanometer, you would have a defect. That costs lots of energy. So instead what they do is just pulling out, and then there's no defect anymore. So this is a heliconical structure. It has no density modulation, but it forms a pitch of about 10 nanometer. So this is the latest nematic phase. After 100 years of first nematic phase was discovered by Reinitzer in 1888, was a chiral nematic phase. Chiral nematic, when you have a chiral unit in your molecules, they make a helical structure, and in this case, the helix axis is perpendicular to a director. A nematic is when you have no chirality in, then you have this nice uniform structure. This was observed very quickly after the chiral nematic. And this is what was just discovered now. This has this twist band nematic phase. And what's interesting is that if you have a chiral dopant or you have a chiral molecule, your helical pitch is in the range of a micrometer. You remember that they have color. And this is non-chiral molecule, and it has a helical pitch is 8-10 nanometer. And we learned that if you put more chiral dopant, the pitch becomes tighter and tighter. But this is the other way around. And of course, because the molecules are non-chiral, you should have left and right-handed heliconics. But we couldn't see that. It's probably in some nano scale. So this is a quite interesting new phase. Interestingly, the materials were known, these dimers, studied 30 years ago, but they were always identified as smectic. The reason because the texture looked like a smectic, and the reason is because you have a 10 nanometer periodicity, which makes a kind of pseudo layering, and it makes very similar structure. So I think after that, again, this one, the first and the last, don't show up very well, interestingly. So I don't know. So here I just acknowledgement to say that the former students who did most of the TM studies were Tsuyu Zhang. I learned that's how to say, but she called herself Tracy. And the guy who did the X-rays, Nick Diorio, and the work was in collaboration especially with Oleg Lavrentovich, whose name came up here, and Min Gao, who is running the TM, and I have a grant together with Sam Sprunt and Jim Gleason, which sponsored some of the work. And then thank you for your kind attention.
Thank you very much. Are there any questions for our speaker today?
We try to quench very quickly. So once it's in the liquid nitrogen, it takes about 1 millisecond to go down to minus 180 degree. And the critical part is then when it's on a heat stage, we use a bench where you can have a given temperature. And then this has to be very close to the liquid nitrogen. So you have to just drop it in. And during that, it's typically less than 1 second, we measure the temperature doesn't change more than 1 degree. So it's frozen in that state.
So when you draw these fibers out of, I guess, the molten state, you probably can't do it in the liquid nitrogen, right?
No. These fibers, what you are seeing is like 180 degrees. Okay. It's just below the isotropic fluid state, just a few degrees below that state. You just have 2 pins and have a drop of that, and then when it goes to the smectic phase, you just separate, and they're just making a necking, and it has a meniscus, and then it becomes completely constant thickness until you have material left. And these are quantized, kind of. One molecule want to make 1.57 micron diameter. The other one want to make 3.2 micron diameter. And it's really amazing. I just don't understand why people didn't pick up, because basically there are 2 groups who are studying those. And we put in carbon nanotubes, and because in the center you have to have a defect. And the defects add to the energy. So the material would be happy to take a single wall nanotube, which is a few nanometer, and get rid of the defects. And we indeed find that you can put in nano tubes, and then the conductivity changes orders of magnitude. So you can play with those things. So we just started working with adding nanoparticles in this materials. Quite interesting, I guess. Okay, for example, this one, or here this. And in this case, actually, you can see the part where in the defect area, this is brighter. So they don't pack that well. But this is smectic. This is smectic. So basically what happens is if you have a small splay, the smectic layers, the layer spacing want to be very constant. And you pay a big price if you want to change that spacing. So if somehow you have a stress which want to splay your layers, then eventually one extra layer will come in, and just to make sure that it has the same layer spacing. And it can do everywhere except, in this defect area.
I have a second question.
Yeah. Please, if you're on a roll.
For smectics, is it fair to say that the layer thickness is very similar, if not identical, to the molecule length?
It is fair. If it's a smectic A, then theoretically it should be the same. But actually it's always somewhat smaller, because there are 3 different reasons why. Even in the smectic A, it's somewhat tilted, but they are just not correlated tilt. It looks like a smectic A. Or there is some interdigitation between the tails. In a smectic C, is considerably smaller because they are tilted away. So from the layer spacing, you can calculate some effective tilt angle, which you can compare with optical measurements. And usually they don't match, but more or less close.